So today we will be designing P, PD, and PI type controllers, but even though I'm saying we are going to design them, this week's code is not going to be, or the algorithm will not be exactly the design steps that we will carry on the upcoming weeks, but it's kind of a introduction level PD and PI controller design, and you'll see what I mean by that. Now, we have an open loop transfer function that is also a second order transfer function with the given parameter zeta equals 1 and the natural frequency is equal to 2. So if I apply, for example, step to this function, open loop transfer function, I will not have any overshoot whatsoever. And omega n is equal to 2. So I can say approximately 2 seconds of settling time will be if we have a step response in front of us. It will track the reference, so I can kind of imagine what the step response looks like by just looking at the transfer function, because I know that zeta is equal to 1, which means critical damped. Omega n is equal to 2. Their multiplication gives me the real part of the poles, meaning -2, and 4 divided by 2, because that's the settling time formula. Even though it doesn't work for zeta equals 1, we can still use it to approximate stuff. So I can say that it is going to be around 2 seconds, the settling time of it. You can also maybe calculate the rise time and peak time whatsoever, but most of the time we are interested in the settling time. So that's all about the open loop that I can say for now. It's the DC gain is equal to 1 because using the final value theorem, limit S times this transfer function times 1 divided by S, they will cancel each other out. You will just plug in S equals 0 here. You will have omega n squared divided by omega n squared, which is equal to 1, which is the gain of the system. Because if the gain is equal to 1 in steady state, we'll see that in steady state, it will track its inputs. So that's that. Now we are going to design controllers that will change the behavior of the system, meaning that it will have a 10% overshoot from this time on, but we're not touching the settling time or other stuff. So we're happy with that, or we're going to be happy with the outcome. We just are interested in the overshoot. It has 0 overshoot in open loop. It will have 10% overshoot in the closed loop. So that's kind of our aim. And we have a relation between overshoot and zeta. In the recent weeks, I've talked about this. I've said that we have a formula. We know how to transition from overshoot to zeta or vice versa. And this is basically it. Normally, you will see something like e to the power of minus pi times zeta divided by 1 minus zeta squared, square root of that sort of formula that's going to be equal to the overshoot. But that is not suitable for design purposes. In this case, we have the inverse formula, where we plug in the overshoot, and based on the overshoot value, we come up with a zeta value that will satisfy this specific overshoot, or that will result in a specific overshoot. So if you see overshoot somewhere, you use this formula, transition into zeta. You don't have, or in this case, we don't have a specific settling time value or anything about the natural frequency. We only know the damping ratio. It means that we're not really interested in the settling time or rise time, peak time values. We're just focused on the overshoot, which means that if we would have come up with an ideal closed loop that would look like a second order transfer function, we only know its zeta value in this case. We don't know what omega n should be equal to. So that's kind of that. Now, and our today's tasks are basically quite simple. They look quite simple. One of them is to design a p-type controller and find everything about the closed loop, repeat it with a PD type controller, repeat it with a PI type controller, and then just compare them. So that's kind of it now. So let's dive right into it. First of all, let's use this relation. Let's define our open loop transfer function and see what's really going to happen. Now we have zeta equals 1, omega n equals 2. So zeta equals 1, omega n equals 2. And our transfer function, open loop transfer function, is ts omega n squared, 1, 2 times zeta times omega n, and then omega n squared. Of course, we are also going to need the symbolic version of this. where we just define it like the following: s squared plus 2 times zeta times omega n times s plus omega n squared. So there we go. Now we have an overshoot value of 10%. And keep in mind that I'm using this percent part 2. So 10 divided by 100 should be plugged in into the formula. So it's going to be 0.1 instead of 10. And the zeta value that is desired for the closed loop is the following: log overshoot. Now, keep in mind that MATLAB is sometimes very weird. If you use log on its own, you know what x1 is, 2.71. So this is natural E. Now, if you use log, therefore, and x1, or maybe 2, for example, you'll see that the log function is actually the natural logarithm. So it's ln, and not the 10 base logarithm or 2 base logarithm. If you want to define a certain base other than E, you just have to provide that number, that base, log 10, log 2. So if you use log 10 and provide 10, you'll see that's basically it. So like log 10 2 is basically 0.3, whereas if it would have been logarithm, natural logarithm, it should be 1. But if you omit this part, it's approximately 1, so you get the idea. This is natural logarithm, not log 10 or log 2. So MATLAB is sometimes weird, therefore we call it log, but it's actually ln. So keep that in mind. Divided by square root of pi squared plus log overshoot squared. So that's kind of the formula. You get used to it when you use it too many times. So let's run this. There we go. Now it seems like we need to define zeta equals 0.5912. If that's the case, it means that for 10% overshoot, we are going to need this value here. And if you remember the fact that if you take the A cos of zeta, actually maybe like this, it's kind of 53.76 degrees. So we only know the angle of the line, the zeta line, and we don't know what omega n is. We don't have any natural frequency. The open loop natural frequency and zeta values are completely different than the closed loop ones. So this is kind of just used as a template. It's not the desired requirements. So we are not designing for zeta equals 1, omega n equals 2. This is just the property of this specific second order transfer function. Or in other words, our transfer function is equal to 4 divided by s squared plus 4s plus 4. So that could have been also given instead of zeta and omega n. But here, the thing is that we want to show you that you are changing these zeta and omega n values. So this change is translated into change of behavior of the system. So we don't know what omega n is, basically. We just know that the zeta value should be 0.59, 5912, approximately. And if you would have used a S-plot or S-domain, if you would look at that, if you would look at the line, it would have this angle here associated to the zeta line. And that's basically what we know at this point. Now, how do we design a p-type controller? Now, as I've told you during the homework part, you can use the root locus command, and we'll eventually use that. But for now, let's try to use the algebraic method. And the algebraic method does the following. Let's first of all define our connection. We have K, which is going to be the controller itself. It's a static gain. And then we will have a closed loop because we're trying to come up with K, GS, and then the feedback loop. So we're trying to come up with a static coefficient that is used with this feedback loop. So we're trying to come up with a certain K value. And if we apply step response from this input, in the output, we should have 10% overshoot. So it's not quite simple to come up with a static gain value if you think about it. So this is the connection that we're after. Therefore, the first step is to just do the math. So K times GSS, because it's symbolic, divided by +1 or 1 plus K times GSS. What we can do is we can just use pretty and then simplify fraction, provide TS in order to see what the closed loop looks like. There we go. Our system was 4 divided by S squared plus 4S plus 4 in the open loop. If we are designing a p-type controller, our closed loop becomes 4K divided by S squared plus 4 plus 4K, 4S plus 4K plus 4. That's our closed loop system. So how can we decide on K so that our zeta value associated to this second order polynomial, the characteristic polynomial of this fraction here, or transfer function, has zeta equals 0.5912. So that's basically the question here. You might want to take a different route at this point. You can maybe try to come up with a solution here. You can try to solve it, for example, and using by b squared minus 4ac, the discriminant, minus 4 times ac. And then you know that if you have the real part, the imaginary part, you can use tangents, and then you can see the relation between the values that you're looking for. That's one way of doing things. But it's not going to be always that easy, because not always are we designing controllers that end up in closed loops that are second order. So this is a very rare case, in fact, because the system itself might be second order, and then we have a certain controller that adds degree to it, and the closed loop becomes a higher order polynomial. In that case, it doesn't really make sense to take this approach, try to solve its roots, and then maybe order it. It will not work. It might work for this example because it's a very simple one, but most of the time, this is not a good idea. An equivalent approach would be the following. We know that our polynomial looks like this. We also know that we use this kind of approach here for these types of polynomials. So we know that we are using S squared plus 2 times zeta omega n S plus omega n squared. The algebraic method suggests that we can use the coefficients of polynomials of both sides, calculate them, equate them to each other. If the coefficients are somehow aligned or are equal to each other, then the roots are also the same. Based on this fact, we can use this approach, equate the coefficients, and try to solve the problem. If we succeed, we will end up in designs. If not, we are going to conclude that somehow it's not possible. Maybe we are missing something, maybe something's wrong, or maybe our specifications are too harsh. We'll see. But the thing here is that we need to decompose the transfer function into its numerator, ns, and its denominator, ds. But let's call them PZS and PCS. The reason for that is that the first one here is the polynomial of zeros. The second one is the characteristic polynomial. So it doesn't really matter, but mathematical notation. So there we go. Now, if we look at this, PCS is going to be basically the characteristic polynomial that we are looking at. Now, let's construct a desired polynomial, because we know that we want to have 10% overshoot, for example. Then what we can do is we can come up with PDS, which is the desired polynomial. Since this is a second order closed loop, we only need a second order polynomial. Therefore, 2 times zeta times omega n times s plus omega n squared would be the desired polynomial. Now, we have calculated the zeta value here, therefore we know what zeta is. But since omega n is not known, we can just define omega n, it is going to be real value, and we can try to solve this. So the problem here is to equate the coefficients of the characteristic polynomial, all the s terms, to the coefficients of PDS, all the s terms. So I'm going to do the following in order to show you what the equations look like. I'm going to cycle through each element of the problem, which are basically equations. I'm going to display them. Problem I. There we go. So there we go. If we have such a system, if we have a p-type controller, if we look for a closed loop, the coefficients are 1, 4, and 4k plus 4 on the left-hand side. On the right-hand side, we have only the omega n value that's not known, but we know what zeta is. We know what 2 times zeta is, so it's basically the right-hand side. So you can see that the first equation here is quite important, because if there is something like 1 equals 2 or 1 equals minus 1, then it doesn't really matter what the other equations are. We are not going to have a solution, because that's not valid. This is a true statement, which is trivial in this case, but which is also necessary in order to be able to solve this problem. It might be the case that there's a certain coefficient on the left-hand side, for example, 4, 4, and 4k plus 4. And then if you try to use it like this, you will fail. You will not be able to solve it. But in that case, only for the highest order term, you can normalize or divide the whole polynomial into its highest order term. And that should happen with PCS. So you should come up with a coefficient 1 here, if it's not 1. But it doesn't guarantee you the solution, because there might be 2 coefficients on the left, 2 coefficients on the right without any parameters involved. Then if they are not aligned, you cannot solve that problem. So you'll see what I mean by that, because it will sometimes come up, and you'll see. Now here we have a set of equations that we can directly solve, in fact, and you can see that omega n is directly 4 divided by 1.182. And if you take the square of that, plug it in here, you can come up with a k value. So we have 2 equations that are not trivial, because this one is trivial, and 2 unknowns, which is an ideal case for a solution. So we can just force to solve it, or we can just go ahead and solve it, and we'll end up with 2 parameters, probably also maybe 2 solutions. I'm not sure. Let's see. Nah, we have just 1 solution. So if we have a struct and there's a field name and then there's something like that, you know that you can access it via sol.k, sol.omega n. And what I like to do most of the time is to define a placeholder for our symbolic variables. K is a symbolic variable, omega n is a symbolic variable, but I'm not going to use the same names. I'm going to use placeholders, which means that it will have kind of a similarity, but it represents the value instead of the symbolic variable itself, because sometimes the symbolic variables will be still in need of use, but then if you override that, you are in a complicated point where you don't have the symbolic variable, but you have expressions that are involved. So it kind of messes up. So don't do that. Just define placeholders for their values. I'm going to convert it into double, sol.k. There we go. Do it for omega n2, sol.omega n. So this means that we can, in fact, we cannot change the settling time or peak time or rise time of this system, because there's just one unique omega n that gives us a certain controller k. Let's first test this. Let's see what the results are, and let me explain in more detail. So fs is in fact k-val itself. At this point, I'm transitioning into the verification step, by the way. This was the design step here. This whole thing here was the design step. Maybe from here. So this can be done via pen and paper. But here, the verification step is going to be the control system toolbox itself, and we'll see what the results look like. So TS is going to be feedback. You can also use fs times gs divided by 1 plus fs times gs, but then you have to use minreal. If you remember, we've talked about this, you might want to use minreal in order to get rid of the pole zero cancellations. But yeah, use feedback if you're using the control system toolbox. And then I can just look at TS but I can also use ZBKTS in order to determine its poles and zeros. And let's actually come up with a figure. Let's have a subplot, 1/2, 1 row, 2 columns, the first one of that. Let's plot the step response on this one. Let's say X label should be time, Y label should be YT, and then the title is going to be the step response. So let's repeat it for the second one, but this time around, let's have sigma, let's have J omega, and pole 0 map, of course, AX2. So let's determine the step response here. Let's plot it. This is going to be the first plot. Let's assign it a color. Let's give it a line width. Maybe also display name. For the display name, what we can do is we can do the following. You might want to use string. You might want to use just this vector here. Let's say P and then the settling time value num to str. This is just stuff that you might want to skip or want to use. Depends upon you. So maybe overshoot is more relevant in this case, but overshoot info.overshoot. And then let's extend it a little bit more. Have that. And then num to str info.settling time. And if I call legend show on this one here, we should have that available. So once we've done that, what we can do is we can just plot the poles and zeros, the poles and zeros, PZ map, TS. So this kind of gives us the poles and zeros. What we can do is we can use real, C poles, and then imaginary, C poles, and then the color. Let's say blue, and then line width, and that should be it, AX2, of course. Let's repeat it for the zeros, even though they don't exist for a p-type controller. We can just take this approach here. So this is quite the visuals. So let's test them. Yeah, in this case, ZPK and TF give the same results because we have complex conjugate pair. It doesn't really show the part. Info, oh, we misspelled info. There we go. Now we have our results. It's too much white, I guess, but you can see. We have -2 here, which is the real part. And we have an imaginary part, which is 2 point, what is it? Can we see it here? 2.72 approximately. So we can see that we have an overshoot value of 10, but our settling time value is 1.75, which we did decide on. This is basically the step response of the p-type controller. What we can do in order to improve this is the following. We can, for example, plot the root locus plot of GS, and on top of that, plot the poles in order to indicate where we are on the root locus in order to see what's really going on. Let me just skip this part, by the way. So there we go. We have this root locus plot, but it stops at 1.5. Let me just take the zoom here, zoom out a little bit. There we go. We can see that we have this root locus plot here, and we are basically on root locus here. If you are in an exam, for example, and if you're asked to solve this question, if this is a problem, for example, and if you know the root locus, you can just see that since you have zeta equals 1, they're on top of each other, and the asymptotes are 90 degrees and negative 90 degrees, there you can conclude that one of the poles will go up like this, and the other one is going to be going down like this. Now, that's important because I have calculated to you that we have 53 degrees. So you can just plot a line through here. That's going to be the zeta line. And you know what the value here, the angle here is, 53 degrees approximately. Based on that, you can just come up with a, you know what this part here is. It is 2. So you can use maybe the tangent in order to just come up with a value, the imaginary part here. And you can also then use the hypotenuse in order to calculate omega n, because the omega n value is basically it's a distance to the origin, and the distance to the origin would give you that value. And in that case, you would be able to calculate omega n, also the k value, because you know that the distance from one pole to this one here times the distance from the other pole to this desired point here multiplied will give you the gain value. So you can apply all the root locus stuff that you know already on this plot, and you can see that it's quite easy to solve it with the root locus plot. But it is even easier to solve it with the algebraic method, because you can directly come up with omega n value without even using any trigonometry. And you can use that value if you have a calculator to come up with a k value. So it's quite easy, but you know, you have to know your second order transfer functions, your root locus, and your algebraic method in order to find your way out of problems. So what we even can improve on this is we can just use the open loop, plot it, and assign it a color like this, for example. And that should be it, actually. We need to copy this part too. So let's look at the open loop values, the overshoot and settling time values, and then design our p-type controller, look at the values of that, and see what's really going on here. How did we change basically the behavior of the system? Let me stop one right. Maybe that's the problem here. There we go. Now, you can see that. Let us also provide a 5 seconds of final time for each plot here, so it doesn't look that ugly. So now you can see that the system originally was tracking its inputs. It didn't have any overshoot. It was basically on this line on the real axis at -2. And we have designed a p-type controller. We've changed its overshoot value, but unfortunately now the steady state value is around 0.6, 0.65 something, whereas the original open loop was tracking its inputs. So that's quite interesting. And its settling time definitely changed, because we have settling time approximately around 3 seconds, as far as I can see, and 1.75 is the new settling time. It's sped up, it's increased its overshoot, but the DC gain changed, so everything kind of changed. The system behaves differently. By the way, we also have something called S-grid. You can use that here. Let me just show you that too, AX2. The zeta value and the omega n value, omega n val maybe, it can be used in order to plot the exact point of interest on the root locus plot here. And yeah, there you go. You see that there is a certain zeta value to it. And you can see that there's also an omega n circle, which doesn't seem like a circle because the aspect ratio of our plot. But there's a half circle here. The intersection of the zeta line and the omega n circle is basically our design point. So you can see that basically, yeah, it aligns with the results. Now, this is the first task, designing a p-type controller. And I hope that you did understand now what I mean by verifying it with the root locus, but designing it with the algebraic method. Because we have still looked at the root locus, and we've seen that it is on the root locus, and the omega n value and zeta values are pretty much correct at this point, because we can see it here and we can verify it. Now, what about PD-type controllers? Now, let's try to design a PD-type controller. Therefore, I might just skip this one here and maybe display a little thing here called P controller, P-type controller. So let's try to come up with a PD controller, or try to design a PD controller. Now, let's talk about the name here first. What is a P-type controller? Why do we call it a P-type controller instead of maybe K controller or static controller? Well, here, if you look close to this connection here, we have R, we have Y, and we have a minus sign here. So we take the difference where this becomes basically E, the error. And then we have the input of the system, and that's basically it. Now, if you look at this part of the connection here, you can see that you can write an equation down, which goes like U equals K times E. So our P-type controller basically uses the error itself in order to generate the control signal here, or the signal that is going to be applied to the system. Now, this is important because the control signal and the error signal are proportional. Therefore, we call this controller a proportional controller because, yeah, they are proportional. And by this naming scheme here, the D stands for derivative. So therefore, we have a proportional part and a derivative part. So yeah, if we know this for a fact, what we can do is we can just say, okay, if we are in the Laplace domain, if we want to take a derivative, d divided by dt, the Laplace of that is basically s. So instead of having the derivative, we will going to have s. And since this is the derivative part, let's call it kd times s, and then plus kp. Now, if you apply this here to this formula, let's have that. Instead of that, we have fs. If we plug it in, we will in fact see that this is the case. Now, if I distribute it, you'll see that KDSE plus KPE is going to be the result here. And you can see that S times E is going to be the dEdt, the derivative of that, times KD plus KPE. So that's basically it. Now, if you think about it, what we can do is we can just have a derivative block, ddt block, and then a KD coefficient, and also a proportional part, let's say KP part, and then that. And of course, they will be they are basically the same. And then we add them together. That's basically the whole point here. And it goes like this. So this is the PD type controller. We have the error itself. We will have the control signal here, U, and it consists of a derivative path and a proportional path, and add them together, and you have your control signal. So that's one way of viewing the PD controller. But there's also another way of viewing it, and that would be to use KD out of the parentheses, which means that S plus KP divided by KD would be the case. And we can just change the scheme a little bit to, because this is a certain thing, and this is a gain. What we can also do is we can just assume that the PD controller adds a 0 to the system and then uses the p-type controller. That's also one way of viewing it. So one version is that we have a derivative part, we add that to the proportional part and take the linear combination sort of and apply it to the system. Another view is that we add a 0 to the system and then design a p-type controller on top of that. So as you can see, there are two unknown parameters that we should come up with. Therefore, it seems like we should have more freedom in designing PD-type controllers. But if you remember or recall from the recent lectures, when we design a controller of a certain order, what we try to do is we try to use the second order formulas. Therefore, there's something called dominant pole placement, where we try to keep all the other poles and zeros away from the dominant region, from the slow poles, and the slow ones decide on the behavior of the overall system. That's basically our strategy. But here, if we add a 0, and if we remember or recall it, adding a 0 in the dominant region is much worse than adding a pole in the dominant region. Therefore, adding a 0 is not quite desirable if it's going to be in the dominant region. If not, that's not going to be a problem. If it's far away on the left, on the yes domain, then you're good to go. But other than that, it might be troublesome. And the problem also is that you are the one who is adding the 0. The system originally didn't have any 0, but you're the one who is going to add it to the system. So if you're not careful with this, you can have some issues. There are also different issues about PD-type controllers because we have a derivative here. So if there's a jump here somewhere in the error, it's going to generate a much higher derivative value, and that also will be multiplied with KD, so it will be amplified. And if you have high frequency noise in your, for example, signals and measurements and stuff, it will be amplified with KD, so it's another thing that we should be aware of. But still, we will see what the PD controller can maybe give us in terms of design capabilities. Because in the previous design, we saw that we have no other choice than picking this point because the only intersection of the zeta value and the root locus is at this point, and using a p-type controller, we can only design this point, and that's it. Let's see what the PD-type controller will end up in terms of, or will show us in terms of, for example, the algebraic method. So if you know this here, you can just keep one of, just choose one of them and use that for a notation. So let me just don't touch them. Let's define a controller. Now let's go with k times s plus z. First, I want to see what this will end up in. So we have k and z, and both can be real, can only be real because our polynomials should have real coefficients. And since we are adding just 1 0, it should be a real valued 1, and the gains should also be real. If it would be a, if we would have 2 zeros, for example, then this could be complex conjugate pairs. But in this case, we have just 1 0, so that's not the case. Now, the algebraic method is nice because we are going to do the same. We are going to repeat this process here. Nothing will change other than the controller structure. And this one can also be copied. So I'm just going to copy them, paste them here. The only change that I am going to do is, instead of k, I'm going to use fs. By the way, our controller is not static anymore. It's not a static gain. It has dynamic parts in it because we are taking the derivative. The derivative is combined with a static part in order to get something else out of it. So we'll see. Now we have added a 0 to system. We have k, and then the closed loop. We get the numerator and also the denominator. Now it makes sense to have PZS because we have a 0. We have added it. Now we have PDS, s squared plus 2 zeta omega n s plus omega n squared. Nothing really changed. We still have zeta equals 0.5912 as a requirement, and we still don't know what omega n should be. And in that case, let's see what the problem looks like. Now, does the order change here? In fact, it does not, because the the controller's order is basically 0. It doesn't have any integrator or any denominator. Therefore, we can just safely assume that this problem here should be displayed. So let's run it and see what the problem looks like. Now here in the console, you can see that the p-type controller problem was like this, and our PD-type controller has the following equations. Now you can see that here we have a k parameter, whereas here it was not really there, it was absent. And we have 4 times k z plus 4 equals omega n squared. And if you count the unknowns, k, omega n, and z are 3 unknowns, but if you don't count the trivial one, you can see that we have 2 equations. Now it seems like we have a degree of freedom. Now we are able to change, for example, or we are able to decide on something here because we have infinite amount of solutions. There's no unique solution. You can just come up with a certain solution. For example, you can choose z equals 1, solve it. You can choose z equals 10, solve it. Choose a omega n value and solve it. There are multiple options here. So this is quite nice if you think about it. The thing that we know is that this z value here should be maybe a greater value than zeta times omega n, because of the fact that it kind of messes up the behavior of the system. We don't want to have a 0 in the dominant region, so we might be careful about that. Now, if we try to solve it directly, if we just rely on MATLAB, which many of you sometimes do in these cases, let me see what MATLAB can offer us in terms of solutions. And I'm not sure that it will be a good one here. So you can see it came up with 4 different solutions, and sol.k gives us, lots of stuff. If you convert it into double, you can see there are multiple options here. We have also z here, also omega n. So it's quite interesting. It found us some solutions here, which are maybe not ideal, but let's try to use the solutions that are calculated directly by MATLAB. Now we know what omega n can't be, so that's not really a value that we should take care of or even use, but we might want to keep the other solutions here. So we have this one here. We might want to also only use the positive k values. So we have to do a little bit of stuff here. So let's get rid of the unnecessary, or maybe not the ones that suit us. First of all, let's say index equals k-val should be positive. And maybe we should also have omega n-val positive. And let's see which ones do satisfy this. You can just use this. Just one AND operator, my bad. So if you look at index, you can see that these 2 solutions satisfy these conditions. You can just AND them and then just get rid of the unnecessary ones. So we can do that by using k-val equals k-val index, and we are going to be ready. So repeat this for omega n-val and z-val. So the feasible ones are k-val, omega n-val, z-val. So z is placed basically on 11.33, but we have different omega n and k values. We'll see. Now, since we have multiple solutions, I'm going to take this verification part, copy it, paste it here. Now, in this verification part, I'm going to have a for loop. From 1 to 2, I know that there are 2 solutions, so I'm not going to mess with that. Or let's even skip that and just do it manually. So let's have fs1, which is going to be kval times tf. Since we have a PD controller, it should be zval. Since we have multiple of them, I'm going to choose the first one here, and then ts1. It is going to be fs1. Let's also calculate the second one here, 2, 2, 2. There we go. Now, of course, get rid of this part here. Also this part here. So let's calculate the first one here. Get the first one. And let's assign it a red color. And this is PD1. Let's get rid of that. TS1. No S-grid. Yeah, that's going to be red. So I'm going to copy this one here, paste it for the second one, TS2, TS2. Let's have a green one. Let's call it PD2, TS2, green and green. There we go. Yeah, I guess it should be it. So let's first of all run it. Maybe I should place a semicolon here. There we go. Now we have different plots now. Of course, if we zoom out a little bit, even a little bit more, is there a green one? Yeah. So interestingly, we can see that first of all, the green one here, the red one here is basically on the same zeta line. So that's nice. But we can see that these 2 solutions, the red one and the green one, are not on the root locus plot of the original system. So that's one thing. Now, but what I can do, and what I'm going to show you in a moment, is that I don't have really this root locus plot now, because the system is not GS for our PD controller. Actually, we added a 0 to the root locus. So there's no 0 in this root locus, so it looks like this. So we should update the root locus plot and see if it's on the root locus or not, because we are adding a 0 to the root locus so that we bend this root locus that these points are on the root locus. So we'll see. So we had zval, and they were identical. Therefore, what I can do is, let me go here, where we call the root locus here. There we go. Now, let's provide a black color to it to indicate that this was the original one. Let's just go ahead and plot a root locus somewhere here on AX1, no, AX2 actually. And GS times TF, since we added a 0, it looks like 1, zval, and 1. Let's don't provide any color in order to see what really happens here. So if you're designing a PD controller, what you are doing is you're adding a 0 to the system. I should be calling the first one because there are multiple ones. So you're basically adding a 0 to the system, updating the root locus or bending the root locus so that the design point is available on the root locus, and then you're choosing the p-type controller part in order to complete your PD design. Now you can see that did we mess up stuff? No. Okay. Now you can see that on the root locus on the right, we actually see that both of the points, when bending this root locus to the left compared to the original one, it is possible to hit this root locus or intersect with this root locus through these two points here. One is the red one here, the other one is the green one, and the line goes through both of them by adding a 0 to this exact point. And we're lucky, seemingly, because the 0 here is far on the left compared to, for example, the red one or the green one. And I suspect that since these two are closer to each other, the green ones, the red one should stick more to the formula or to the second order behavior than the green one here, because as far as the 0 gets, the better the solution, or the closer the solution becomes to the second order behavior, or the formulas get more correct. So it is important to see that this is the effect of a PD controller. You can add a 0, bend the root locus so that it goes through the zeta line, and yeah, basically have these outcomes. We can also see that since the formula is 4 divided by the real part of the pole pairs, we can see that this value is a lower value and this is a higher value. So the real value of the red one is greater than the one with the p-type controller. So having a greater denominator, or in the fraction 4 divided by zeta omega n, means that it will be a lesser value. So it's going to be faster. And since this is more on the left, the green one is even more faster than the red one. And you can see that. You can see the effect here. You can also look at this legend here and read the values here and see if it's really like that or not. By the way, you can see that the PD type controllers don't end up in exactly 10% overshoot. They are a little bit off, and the green one is more off, and that's the reason why. Because the dominance factor here is lower on the green one, because they are closer to each other. They should be further apart from each other. So the red one works better. And you can see the red one is slower, but the green one is faster, but then it's not exactly 10%, but the other one is closer to 10%, etc., etc. But it is possible to speed up the system and try to design a PD controller by adding a 0, altering the root locus, and then choosing the p-type controller on top of that. But again, be careful. You added a 0, you should be further away from that. But then also you want to be faster, so you want to also approach to the left. So it's kind of a interesting thing. There's a bottleneck here, because you might want to get faster, but you hit the 0, and that's not a good idea in terms of the transients. So the PD type controller has also steady state error, by the way. You can see that the P controller has, the PD type controller has, and that's the nature of it. We cannot avoid that. So yeah, of course, this is not the ideal design method for a PD type controller. We've just arbitrarily chosen to to different solutions, and we just stick with MATLAB solutions. Don't ever do this. Never ever do this, because this is not ideal. This is just to demonstrate you that there are two solutions, for example, that even MATLAB can handle and give us, but there are infinite amount of solutions. Maybe there are better solutions than these two red or green ones here. So yeah, keep that in mind. Now, our last question here, because we are already comparing them, is C, design a PI type controller for the given requirements. Now, before I go on with that, let me also remind you that actually, when you're in an exam, or if you are trying to design a controller using the algebraic method, it is not really a good idea to use this notation here, because this notation favors the root locus. If you want to use the root locus methods, adding a 0, determining the location of the 0, and then coming up with a p-type controller makes sense. But in the case of algebraic methods, I would suggest that you, instead of defining it like this, define it like kd times s plus kp. And I'm going to show you why it's relevant in the PI case here, but you'll see that there's a multiplication k times z, and it arises in the equations. And it seems like this is a highly nonlinear set of equations, whereas if you define it like kd times S plus KP, what you would see is this would be 4KD plus 4, and then 4KP plus 4 would be the left-hand side of this set of equations. Of course, since we don't know what omega n is, it seems to be still nonlinear, but it's not really that hard of a problem. But if you use the this notation here, the algebraic method seems to be nonlinear, but that's not really the case. So let's apply this information here during the API design. So based on the same approach which we did here, this is basically the proportional dash integral controller. Now we have an integrator. But in terms of poles and zeros, the only difference between a PD controller and PI controller is that you have basically the PD controller, but you divide it with an S, or you have a PD controller times an integrator. So it's important to know this too. So this is basically adding an integrator with somewhere here, for example. If you think about it, we have KDS plus KP divided by S, and that's it. In terms of poles and zeros, now we are adding a pole at the origin to the system, a zero somewhere on the left half plane, and then choose a p-type controller in terms of the root locus methods. But in terms of using the algebraic method, this wouldn't be recommended. I would recommend you to convert it into the following. If you look closer, this is basically K times S, K times Z, and then divided by S, divided by S. So this cancels out. K plus K times Z divided by S would be the thing, but renaming it to KP plus KI divided by S would make more sense. So this is basically it. We have a proportional part, as it is in this case, but we have an integral part, and we have an integrator 1 divided by S, or yeah, the integral ddt. So we are calculating the integral of the error multiplied with Ki, Kp times the error, and then just combine them into a control signal. That's basically it. This one can also be written down like this. Kp times S plus Ki divided by S is also a way of defining it. So actually, again, I'm going to take this approach. Let me just copy this one here up to this point before we solve it. So now, of course, I'm going to define it like Kp and Ki and see how easy it becomes. So if you're new to the PI controller, you might want to use always Kp plus Ki divided by S, because this makes more sense. We have this one here, PZS, PCS. Now we will run into a certain problem, because the system originally was a signaler system, and then we added an integrator with a controller to it. So it means that we will have a third order closed loop. In that case, we added a pole and a zero. So the closed loop will be 1, 0, 3 poles closed loop transfer function. And therefore, we have to add another polynomial in order to be able to equate the polynomials to each other. So we need a residue polynomial. Now, designing a PI controller is harder than designing a PD controller, if you think about it, because we have to push away a pole and a zero instead of pushing only a zero away from the dominant poles. In the PD type controller, we didn't add any poles, so we didn't have to care about that. We just have to keep the zero away from the dominant poles. But here we add a pole, a third one, to the system specifically, and a zero. Both of them should be far away from the dominant poles. It becomes harder and harder. But let's see why we even bother with this system here. Of course, PDS on its own will not be enough to equate this polynomial to the other one. So the multiplication PDS, PES kind of is necessary at this point. Let's call it PI controller. And let's see what the problem looks like. There we go. Now we have more equations because the order of the problem increased by 1. And yeah, on the left-hand side, you can see the advantage here. 1, 4, 4kp plus 4, and 4ki, and that's it. You might argue that this is not linear because of omega n. I would say, okay, you're right, but it's only because of omega n. If you know the settling time, rise time, peak time of this system as a requirement, at that point, omega n would vanish and everything would be linear. You can check it out. But in this case, it's not the case. So yeah, we have to deal with it. But you can see at least the controller parameters or the left-hand side of these equations are linear. So that's something at least. Now, we have P, omega n, Kp, and Ki. So again, we have 4 unknowns, but 3 relevant equations. The other one is trivial. Therefore, again, we have infinite amount of solutions. So we can again rely on MATLAB, which is only be happening this week, because then we will look at the optimal design of these controllers. So this is not optimal at all. It's just a solution, not the best solution in any sense. So we're just trying to solve it, nothing else. So of course, now we will have Kp val, Kp, and then omega n val, omega n, Ki val, Ki, and P val, of course. So let's see. P val, Z val, P val, omega n val, Z val was PD controller. Kp val, Ki val. There we go. Now, of course, it's interesting to note that MATLAB tends to equate stuff to zero if it's not necessary, because, well, there are infinite amount of solutions. It gets rid of omega n by setting it to equal to 0. If it does that, Ki becomes 0 and solves it. But is this an applicable one? Of course not, because Ki is 0. So it reverts back to the p-type controller because Ki val is 0. If you plug in 0 here, you have Kp only. So it doesn't really make sense to rely on MATLAB in this case. So what we can do is basically we can decide on a certain parameter. In this case, let's decide on omega n, and so we can see if it's going to be a good choice or not. So what were our settling time values? Let's see. Well, 0.6 seems to be the fastest one. So let's try 4 divided by zeta times 1. Let's say we want to have 1 second settling time. So I've just arbitrarily chosen settling time equals 1 and plug it in here to get the omega n value. I'm going to use that omega n value and see what happens now. So P val, Kp val, Ki val. Now, sadly, I can see that P val is -4. Now, up to this point, we didn't even argue about the stability of the closed loop because we had only PDS. For the p-type controller, it was just PDS. For the PD-type controller, it was just PDS. And PDS, by definition, chooses zeta positive, omega n positive. And if you have positive coefficients for a second-order polynomial, the solution will be stable, always. But if you have a third-order polynomial, that's not the case anymore. I'm sorry. And if you solve the residue polynomial, you would see that S is equal to -P. And therefore, if P is positive, then the whole closed loop system would be stable. But in this case, we have -4, which means that this would be a right half plane pole. We're not happy with that. So I have to change the settling time a little bit. Maybe a slower one would help us. I don't know. I'm just trying it here at this point because it is not given. So let's see what p-val is. P-val is 0, still not a good idea. What about I don't know, maybe 0.5 seconds, maybe a faster one. I highly doubt that, but let's see. Nah, it's not working. Let's make it 3 seconds. There we go. At least it's a stable solution. Now we have 2 poles that are dominant, and then we have a pole at minus 1.33. And these are the Kp val and Ki values. So we can see that this would be then basically the controller parameters. Now I can just go ahead and copy this part here, I guess. Yeah. So now we only have one solution at this point, so I can just say FSPI, maybe something like that, TSPI, and it would look like this: KP val, KI val, and then 1, 0. And FSPI, there we go. Now I can also update the root locus here. Now I have to look for KI val divided by KP val. If you look at this, if I factor out KP val, 1 KI val divided by KP val, this would give me the 0. Therefore, I'm adding this and also a pole at the origin, 1, 0, because this is added to the system. And on top of that, we are trying to design a p-type controller. So let's have TSPI. This is a PI controller. Let's get rid of that. TSPI. Let's choose a color. Let's call it magenta. And I guess we should be good to go. Yeah. All right, let's try out. So there we go. Now, in fact, we can see that, of course, we have overshoot. And in this case, the overshoot is 7.44. The settling time value was, I guess, 3 seconds in this case. Yeah, I've chosen it to be 3 seconds. And luckily enough, it's quite close to it, 2.57. And on the right-hand side, you can see that the root locus plot is altered differently this time. We can see that a pole 0 pair appears here, and therefore it is bent to the right. And you can see it became slower for that matter. So this is a slower response, but it did the job. You can see that there's a certain overshoot. And yeah, in terms of dominant pole placement, this might be not so ideal, but the fact that the pole and 0 are close to each other is quite a nice thing. And we can see it by looking at TSPI in the ZPK form. We can see that one is at 1.46, the other one is at 1.33. So they're close to each other. So they cancel each other out in terms of the effect. And once they cancel each other out in terms of their effect, we get just the second order part. So this is somewhat a good solution. But if we would calculate the dominance factor, of course, that would not be an ideal value. But if we neglect the pole 0 pair, then, of course, we have a good dominance factor. And pole 0 cancellation is a nice feature in this case, because we might get rid of the unnecessary parts here. For example, this pole and 0 here. But they are still necessary in order to just bend the root locus in such a way that we get the desired results. By the way, we did alter its overshoot, but we could also somewhat decide on the settling time of the system, which means that this degree of freedom helped out in just designing a controller with 2 specifications using the PI controller. And it is also important to note that the reference tracking is back. So none of these controllers, the P controller, both PD controllers that we came up with, couldn't track the reference inputs, but the PI controller did. So it is important. Therefore, most of the time we deal with PI and PID type controllers because they can track the step type references. So this is basically it for this week. And I have, of course, all the documentation and stuff available in the PDF. But keep in mind that this is not the ideal design of these controllers because we didn't have any objective whatsoever. We were just looking for any feasible solution for these controller designs. And you can see that knowing the root locus, knowing the algebraic methods in conjunction with each other is quite important. You have to know both of them, one to verify the results, one to maybe comment on it. You can, for example, see that all the solutions are on the zeta line, which is the only prerequisite that we had here. But yeah, I can see that if it's moving towards to the j omega axis, it becomes slower. If it's moving away, it is faster. But then there's something called the dominance factor. If the residue poles and zeros get closer to the dominant ones, then basically the formulas are not that applicable anymore. So it has its pros and cons in using the dominant pole placement methods, using the algebraic method for solution. But yeah, it is what it is, and we can see that it works for some cases. For this specific case, it seems like the PI controller is a good choice, but we have to determine the setting time in order to come up with a design here. So in the upcoming weeks, we will be attacking this problem in terms of the optimality of this problem. Not just for any, we are just not going to look for any feasible solution. We will just try to optimize them in a certain way. So this is it for this week. See you in the upcoming weeks.